Okay, so welcome to this next lecture in some examples. Today we're going to look at examples in prebiotic evolution. Particularly, these are going to be very strong simplifications of fundamental problems and that even still today are a subject of debate in the scientific community. But we're going to reduce this into the most simple cases and try to understand some of the very basics that we can tackle with our methods in dynamical systems, right? So to begin with, we are going to take the following problem, right? So we have studied already passive diffusion, or sometimes just called diffusion between two compartments. And now we're going to take it a little tiny step further by introducing the following idea, which is sometimes called active transport, right? Consider in this case that we have, for example, a particular membrane. This could be a membrane in a protocell or a cell itself, right? These membranes sometimes are populated with specific enzymes or protein structures that are sitting right on the membrane, such as this one over here, that allows for the following process to happen, right? Imagine that this is the outside of the membrane here, schematically drawn, and then this is the inside of the membrane, and we do have some specific metabolite or a biomolecule on the outside that the system wants to take inside and inject it by this enzymatic process somehow. Right? So we will consider that this is happening at a particular rate, mu, and provided that there is the presence of this protein P. Okay? In the meantime, we will not forget about our good old diffusion process, which is happening in the background, and this is here depicted, right? Remember that in diffusion between two compartments, we have approximated this process by saying that there will be, with rate d, there will be transitions from the compartment on the right-hand side to the left-hand side, and equally from the left-hand side to the right-hand side, right? So this is depicted down here. Now, let us see how the ordinary differential equations for this simple expansion on the usual diffusion process look like, right? Using now the fact that there will be these proteins that, very importantly, are allowing us to distinguish between the two compartments, whereas before we couldn't do that. Okay, let's see how the equation shall look like, right? So to start with, I am going to denote by x the concentration of biomolecule on the left-hand side. And I'll do the same as y on the right-hand side. All right, so let's say this shall now look like the following, and I'm going to go a little bit faster here because we have seen this before, right? But basically we'll have this term that it's coupled to the gradient between the two compartments. So if y is larger than x, in this case, then there will be natural diffusive flow from y towards x, and accordingly, when I'm looking at the concentration on the right-hand side, namely the y variable, I'm going to have the same but inverted, right? And naturally, if it's the other way around, if it's x that has a larger concentration, this means that there's going to be flow from the left-hand side to the right-hand side, and so on and so forth. So far, these equations, we know them very well, we have worked them out, but now we need to introduce this active transport term, right, that it's given rise through this particular enzyme here. Okay, but now we have to be very careful, because what's happening here is that this enzyme has a direction. It only works, the flow only works one way, right, thanks to these different processes. Well, then we have to see that when I am activating this transport, the left-hand side is going to be depleted from this specific metabolite, and therefore I should add here a minus sign, use mu as its effective rate, also denote that there will be the presence of this protein for when this is happening, and what I'm going to do here is I'm going to be depleting from the compartment X. That's the only way that this specific example works, right? Now, on the other hand, I am also going to have some implications from this active transport on the Y compartment, the right-hand side one. But this one is actually going to be positive, right? Because we are receiving an input of these biomolecules. But it's going to be the exact amount that I am depleting from the left-hand side in this case. So notice that this is going to have this specific term, right? So see that now these two equations are not symmetric anymore, and we are going to explore this asymmetry a little bit further, and then we'll draw some interesting conclusions out of it. Before we go on, we will assume that there's no creation or destruction so far for this specific biomolecule. This allows us to write down a constant population constraint, which I'm going to just take it normalized to 1 so that the equations are going to be easier, right? So now we have all of our ingredients and we can move on and try to solve the problem, right? And to begin with, let us focus all our attention on the left compartment. Let me also add here before I forget that we shall have some initial conditions, and we will explore the following problem, which consists on having all of the metabolite or this biomolecule on the left-hand side. So all of it will be sitting on the left-hand side, and we want to see what happens as I turn on this little device, and both diffusion and this active transport are activated, right? So if we have this, notice that due to the constant population constraint, we naturally must have that the concentration on the right-hand side must be 0 at the beginning of this experiment, so to speak. Now we do have all of the ingredients that we need to move on forward with, but we will focus our attention on variable x. Notice that when I'm focusing attention on variable x, this I could have done the other way around, because thanks to the constant population constraint, anything that I now know from variable x, I can translate to variable y just by a simple transformation, okay? If I do focus on variable x, notice that I can take this equation, and using, again, constant population constraint, I can write it as follows. And I'm going to move a little bit faster here so that we don't lose ourselves in the details. But this you should work out yourselves in a couple of minutes at most. Okay, so what have I done here? Basically, the first thing I've done is I've taken y and I substituted this for 1 minus x. Notice that this is going to give rise to a term that looks like 1 minus 2x, which is this 2 over here. Okay, so what's this alpha? Well, I will define alpha as follows. So this is a definition, this is a parameter that I'm renaming, just because it'll make algebraic manipulations easier. But notice that basically what I have done here is I divided this term by v and multiply it by v, the diffusion constant. And now I have been able to take v here as a common factor outside of the brackets. So naturally, this maps directly into this through the constant population constraint. But this equation, I do know how to solve. This is actually a very simple equation we've been seeing all along these lectures, time and time again. Okay, so let's move down here and try to solve this equation once again, right? So I'm going to try to do this pretty fast. Basically, what I'm going to have to do is I'm going to have to integrate from the initial conditions until a time t. Notice here I'm going to basically separate variables, just as we've been doing all along. And this shall look like the following. See how now alpha is, because I don't have to write this cumbersome set of parameters, this is kind of making my life tiny bit easier. Right, on the other hand, we should not forget about this d over here that's sitting right from this factor, and then we are integrating over t here. Nothing new, we've seen this before, and now I'm going to just move on to the solution of this integral, right? Well, first let's do the solution of the integral. Notice that here there's going to be a factor, right, that's going to come out on the right-hand side after all. So there will be some steps in between if you like, but you can definitely work them out yourselves with no issues at this stage. Remember that the initial condition, such as we have defined it, is that x at time 0 is going to be 1, right? If you were trying to solve this problem using the concentration on the right-hand compartment, namely on the y variable, you should have been careful here, because then your integrands would look a little bit different. But again, remember that if you do it either by x or by y, you're basically going to be able to transform from one another. In this case, this is what this integration process would look like with this 2 plus alpha term over here. Remember, this is coming actually from the integration on the left-hand side, but I'll just put it in the right-hand side. And after a few algebraic process, I will jump straight forward to the solution, both for x and y, so that we can see what this entails and how this shall look like as functions over time, right? So here, you're going to have the solution for x of t, which I am just isolating from this simple equation here that we obtained by solving the ordinary differential equation. And it looks like the following. Be careful here when you do this calculation yourself. You must do this calculation yourself so that you are certain that you don't commit mistakes. And you get also a hand of it. Right, so this is going to be for xt. Remember, for yt now, all I need to do is take this simple subtraction. This is just a matter of, okay, like plugging in and then taking a common denominator, so on and so forth. But this is what you shall get at the end. And now we're going to explore some limiting behavior. Okay, let's see. Right, so, all right. Now that we have this, first thing that we can do is just plot how this looks like, right? And I'm going to plot it right here. First off, this is going to be both x and y, right? And this is going to be time here. Notice that we have started, so if this is x, we know that x starts at 1, whereas y starts at 0. Okay, I'm going to use colors for this. So let me use these two colors. For example, x is going to be drawn in blue. All right? And y is going to be drawn in yellow. Great. We know that x will start here, y will start right here. And if, let us just think now before we draw anything, if there was no proteins, no enzymes on the membrane that allowed for this active transport, then what should we expect asymptotically? Well, we know this result because we have studied it before. We should expect both compartments to equalize, right? To become of the same concentration. In other words, half and a half. That's what happens when you have two compartments with just passive diffusion working in it. But this is not what's going to happen at this case, right? So we have to see that in these particular solutions that we are now written, if I take let me write it like this. If I take the limiting for t for large times, what am I going to see here? So in this case, notice that this is going to vanish, and I'm going to be left with 1 divided by 2 plus alpha. If alpha is larger than 0, right, then this is going to be a bit lower than 1/2. Only if alpha is equal to 0, I shall get 1/2, but alpha equals to 0, we'll see next, actually corresponds to having just a passive diffusion case. Otherwise, from here, I can have the same calculation done, basically taking the limit for large times, and what I'll get is, very simply, 1 plus alpha divided by 2 plus alpha. Notice that this can be attained by quickly looking at this inside this bracket, and notice that this is going to vanish for very large times. Great. 1 plus alpha divided by 2 plus alpha is actually something that's a bit larger than 1/2, right? And we can now plot what this shall look like. So basically, we're going to go like this, and eventually, we're going to reach some asymptotic behavior over time. And this value right here, this value is going to be this x star, right? What will happen for y? Well, for y, we're actually going to see something that it's pretty much the opposite, okay? Notice that I do know that this must cross right at 1/2, because all the time I must conserve the constant population constraint, which I rewrite over here, which is that they always have to add 1. So now we have also this asymptotic behavior, which in this case we know that is going to be exactly for the value y star. Great, so this is how the schematics of these two functions work. So we know that if you start your system with all of the metabolites on the left-hand side, these are going to be lowered and lowered over time, and then you'll eventually cross and have this differential, notice this differential or this gradient of concentration activated and actively maintained through this enzyme of active transport, right? So notice that there's going to be a gradient here. This should be symmetric, but my skills at drawing on the blackboard are lacking. Okay, but these two separations here shall be symmetrical. Okay, you can also prove that if you want. Finally, let me discuss some of the limits that we can attain from looking at these expressions. No? For example, I could consider what I call the diffusive or diffusion, let's call it diffusion dominating regime. What is the diffusion dominating regime? Well, the diffusion dominating regime will simply come from observing the problem where d, the diffusion constant, is much larger than the constants associated to the active transport. Remember, what were the constants associated with the active transport? Well, basically, they were the efficiency at which the active transport was working and the number, if you want, or the concentrations of enzymes on this membrane, right? So if we are under this scenario, consider what happens to alpha. Remember, alpha is mu p times, over d. Which means that if I am under this consideration, I shall take this limit, right? Where alpha basically goes to 0. This is what's corresponding to the diffusion-dominated regime. But if I take these solutions and I consider this, and I'm going to call this I for the first regime that I'm considering, right? For this diffusion-dominating regime, when alpha is 0, all I get here is that this tends to 1/2. And similarly here, for 1 plus 0 and divided by 2 plus 0, this is again just 1/2. And notice that this is telling us that for diffusion-dominating regime, as we should have expected, our solution will tend to equal compartmentalization and no gradient. There will be no gradient of concentration. These two lines will just correspondingly go down asymptotically to 1/2, just as we should know and we have predicted before with classical diffusion. But let's consider now the opposite, right? Let's consider that we are in the, let me write it here, active transport dominating regime. Right? In this case, what we shall say is that the diffusion constant, the diffusion rate, is way smaller than the active transport constants that are governing the active transport process. This translates naturally from the same sort of argument to performing some sort of limiting behavior such like that. Let's call it this the second regime that we shall explore. In the second regime, I'm going to write it over here for lack of space. I am taking this large alpha behavior. This means that x star is going to be looking like 1/alpha. In other words, this should be looking like, because I can just now ignore these two here in the denominator, this shall be looking like something like v over mu times p, right? So if I were to be a bit more serious about this limit, this shall just strictly go to 0. But I want to show here how is this actually approximating 0. On the other hand, for y, this means that both the 1 on the numerator and the 2 on the denominator can be basically ignored, and all we have is alpha over alpha. We could actually expand this with the Taylor series over infinity in this case, or take 1/alpha, name it another constant, and expand it over 0. But all in all, what I try to say here is that this is going to tend to 1, right? So asymptotically speaking, for this active transport dominated regime, what you shall have is that this gradient will be maximized where the yellow line goes up to 1 and the blue line goes down to 0, right? Or almost down to 0 as we approach very, very large values of mu times p. Okay, so now we're going to discuss a little bit further. We're going to include these examples into protocells. So for that, I'm going to erase the blackboard, and we're going to come back to it. All right, let's now move on to actually ask ourselves some of the consequences of the existence of this biological trait in membranes that allow for active transport, right? And then maintain these gradients between the outside and the inside. But now we are going to look at protocells as an example of what kind of things can happen when we allow for this to occur in our system. In this case, we're going to look at protocells in general, in a very theoretical way. And we shall consider, for example, as a protocell, some sort of a membrane or a vesicle, right, that can distinguish the outside from the inside, right? We should, for example, consider that the outside is pretty large and very well mixed in a way that it can keep a concentration of whatever biomolecule we are looking at. In this case, I am drawing this as small points right here. We should be able to consider that if the outside is pretty large enough and well mixed, this concentration of molecule could be just a constant, right? This differs already from the problem that we were tackling before, but still we can look at it and try to answer some very basic questions. Now consider the inside, right? So in this case, this vesicle, this protocell, we have included some of these active transport, membrane active transport enzymes that allow to draw actively some of these elements from the outside towards the inside, right? So some of these molecules that we're going to be looking at. In particular, we could denote the concentration of these elements, C sub I, for the concentration of the inside of this protocell, right? We could also allow for diffusion, passive diffusion, to occur between the inside of the cell and the outside with some constant D for the diffusive part. But we can even think further, right? And this starts to go to the core of some of the issues that people are looking at in the context of prebiotic evolution, which is what kind of reactions should I expect to have inside of the cell, and what does this could entail for when it comes to things like replication, right, or duplication of cells. So we shall talk a little bit about more of this towards the end of this exercise. For now, let us just consider this very simple problem and consider that in the inside of the cell, not only am I able to introduce actively this particular metabolite or this specific biomolecule, but also I can transform it with some rate r from, in this case, just for depiction, from this dot-like molecule to this square-shaped molecule, wherever it is, right? So in this case, if my variable of interest is the concentration of that particular molecule, the one that looks like a round here, over time, we shall try to define some ordinary differential equations for the concentration of these over time inside this protocell. Now, considering all of what we learned, right, notice that one first approximation that we're doing in trying to describe this system is that this protocell will be able to do this without any major development in its volume. We'll see later that this actually is what's it's the precursor of some of the issues such as replication. But for the purpose of this exercise, we shall consider that the volume is not changing, and therefore all the different behaviors for the concentration as a variable will be due to diffusion, active transport, and the actual reaction within the cell walls. So let's start with diffusion. We know that from diffusion we shall differentiate from the outside compartment. In this case, it's just the environment, with which we've mentioned that its concentration is going to be taken as a constant. So we know that this shall be our diffusive part, right? So if the concentration of this metabolite outside is larger than the concentration of inside, I know that through this diffusive process I will be able to inject, or if you want, absorb passively some of these biomolecule. But on the other hand, I do have a number of proteins, right, that are doing the same job in an active way through some efficiency or rate, namely mu. In this case, we need to be very careful here because what this is gonna do is going to inject, so therefore there's going to be a positive term here instead of a negative one. We need to be very careful when we write these equations down. And basically it's going to be taking material from the outside towards the inside. We have this plus sign, and we need to couple this to this concentration, which is the outside concentration, the one that it's being depleted. All right. Finally, because we have also introduced the idea that there could be some reactions happening inside the cell, we need to consider what happens when I am transforming, in this very simple example, this metabolite into another one, right? This other one, we are not looking for its concentration. We are basically interested in this problem in trying to know the concentration of this one. Therefore, because this is effectively going to deplete the number of biomolecules inside the protocell, or basically it's transforming them, we shall write this term, right? Remember, this is just a simple linear decay for the concentration of this metabolite. So now we do have the whole equation, and we could, for example, look for fixed points and look at its stability, which pretty straightforward we can obtain. So let me just go down here, let's take the same equation, and now we are going to rewrite some of the terms in a more succinct way. So for example, I can have C naught here, and notice that I shall have this as two terms that will share this C naught. In this case, I shall write this. Right? So this is going to be just an overall constant, whereas all the terms that carry Ci can be rewritten as follows. Right? So this very simple setup already is telling us that there is going to be a fixed point. And already, because we have solved this equation over and over again, we know that this fixed point is going to be an unstable one, a stable one. Let me be clear. And we don't even need to work too far here, because we see that this is just a constant and this carries a negative sign. And so if I were, for example, looking at perturbative analysis, or if I were to take the derivative that corresponds to the Lyapunov coefficient, we know that for the variable Ci, everything will go away except this term here, minus d plus r. And because all of these two constants are positive, minus something positive, it's going to give me a minus sign. So I'm saying this by words. You might write it down yourselves so that you understand what I'm saying. But from this simple looking equation, I already know that the fixed point that I'm calculating right now is going to be stable, right? And the fixed point, remember, it's just obtained by considering that there's no further evolution, that the derivative of the concentration inside over time is 0, which leads us to the following fixed point that we have already argued. It's going to be stable, right? Okay, this is rather interesting. This is telling us that we can achieve, by these simple rules, we can achieve some homeostatic state for the concentration of this metabolite or of this biomolecule inside this protocell. And this is important because we know that in biology, homeostasis is one of the major features, right? It's something that it's very important to achieve and to maintain somehow. But again, this might be a very, quite an unrealistic process, because, for example, as we are moving material inside the cell, naturally this cell will be more crowded, and therefore we should expect something else to happen. For example, the volume shall increase, and when the volume increases, it also the surface also increases. And actually, let us just discuss some of the different features that could happen, right, with these very simple schematics. For example, one of the things that could happen is that instead of having this sort of reactions inside the cell, I could have different sort of reactions. So for example, why not, I could be thinking of, all right, imagine that instead of one molecule transforming from a dot-like molecule into a square one, in actuality what's happening is some process of dimerization. So for example, I am absorbing monomers from the environment, but then inside the cell what's happening is that these monomers are performing a reaction that allows for dimerization. In other words, this is turning into pairs to something that maybe looks like this, right? Or if you want, some other molecule that it's now a dimer. If you consider these sort of reactions, then this scheme no longer applies, and you have to think a little bit farther, right? And this is something that I will leave you as an exercise that you shall do, and you have already the PDF files to do so, right? So consider this example where I could actually devise other types of reaction happening inside the protocell. But even we could go farther and start coupling these reactions to the same surface. And this is something that scientists are now trying to look at and try to understand how this might have strong implications for issues like the origin of life or the origin of cellular replication. Right, so in this sense, let me just depict here what I try to mean. Imagine that what we have is we are introducing a number of monomers of some sort or some particular biomolecules from the environment towards the inside of the cell, but this allows for some transformation that eventually, after maybe a few biochemical steps, we get the actual proteins, lipids, or whatever that are sitting on this surface, right? The different molecules that could be performing the function of sitting there on the membrane. So these would be membrane molecules. And basically what we are seeing here is some kind of a closed loop where I am absorbing material and I am using this material in order to generate more and more wall for this compartment that we are calling protocell, right? So this, for example, it could go into, right? So imagine that this is some sort of a look at my membrane, right? And there's a gap here of sorts. Right? So this could actually fill up this gap, right? Right? And therefore, we could be growing and growing the cell in a way. When we're growing the cell, there's a number of things that our equations shall change in many ways. For example, if the cell is growing, then the concentration of the particular metabolites that we are looking at, it's going to be affected by that because there's going to be more volume. And the more volume, we know that there's going to be less probability of them to interact with each other. All of this starts to interplay and imposes a different approach when we want to tackle this problem mathematically, that it's beyond the scope of this course. Because now we shall have more than one variable that is varying over time in a coupled way, and we should need to use further methods that are not available for us right now in the course. But I want to point out that this is sitting at the basis of something that is an active area of research, and its basic problem is to try to see when or what is the minimal requirements that are feasible, chemically speaking or biochemically speaking, for which I shall have some sort of vesicle system with all of these features that I've been discussing and maybe some other further features such as potential active transport enzymes on the membrane, different concentrations of different metabolites inside or different biomolecules, whatever you want to call them, and by which the different rules that are connecting all of these elements, what you shall obtain is something that should be looking at a process that over time, right, generates two protovesicles and initiates some instability process that should be unstable in the sense that it cancels the possibility that this cell keeps just growing, right? And forces it to be divided into two, and that would be, if you want, a precursor for cellular replication. But it should do so in a way that it doesn't become too unstable or too rugged and therefore explodes or loses its capacity to maintain this compartment, right? And so this is still an open problem. These sort of questions began to be studied many years ago. A lot of people have played a big role. There's some that may have passed under the radar. I just want to mention Nikolai Rashevsky, who actually started these developments back in the 1930s and 1940s, looking at very simple setups where the kind of equations that he was looking were very close cousins of the ones that we have been exploring right here. And finally, you shall have some papers that I am also referencing in the notes that make mention of this sort of issues in the prebiotic scenarios or in the origins of life problems that are still part of active research that look at the following duality, which is metabolism versus information. What do I mean by that? There's still the question, what comes first in prebiotic evolution? Is it some sort of metabolism or physicality of processes such as this one that I am describing here, where you might have some vesicles that are sort of devoid of molecular polymerized information, but they are able to compartmentalize and undergo this sort of division process? Or was it something like information, meaning some proto RNA or DNA, probably not these specific molecules, but a polymer that can have some information encoded in it that allowed for these systems to be regularized, right? So this is still an active area of research, and I would like you to go on and read these references yourselves and try to think about these questions. Okay, so our next example will concern a very simple model, very simplified model of some very important issue also in current research and research in the past few decades that concerns polymer growth dynamics. Okay, so we're going to look at a very simplified model of such an interesting biological process. What should we be looking at? Consider there's like a soup of monomers that's floating around, all right? They are floating around in some specific area or space, and we have a finite number of those monomers. We will consider them to be just finite. So let's say that we have a total number of n monomers floating around in this space. But there is some if you want, nucleation or starting point at which these monomers start performing structures. And these structures, it basically could be thought of as these different monomers attaching each other and generating what it's often called a polymer, right? So this would be one of these such examples. In general, we could have ramifications such as the ones that are drawn here, but we are not going to delve into those specific details for the purpose of this exercise, okay? So now, the important aspect here, the thing that we have to remark, is that once these constructions start to form biochemically, there will be some sort of a feedback reaction that basically tries to absorb more of the monomers and keep building up this polymer, right? So the polymer will sort of autocatalytically enlarge itself, right? We're going to draw a diagram very shortly trying to explain that. Not only that, but also these monomers sitting inside the polymer are not that stable. So it could so happen that, for example, in this particular case, this monomer, with some rate, it detaches from the polymer. Notice that in order to actually do a serious simulation or a serious model for these systems, we should be able to track the length of the polymer. We should be able to explain precisely what types of monomers are going to detach from the polymer. But we are going to reduce this system a lot so that we can actually explore what shall happen in a sort of a mean field or general approach, such as the ones that we have been exploring all along the course. In order to do so, let us consider the following diagram that is a basic depiction of what I've been explaining here. Suppose that we have C to be the concentration of or if you want the total number of free-floating monomers, right? And we just call this the compartment C, right? And let us call P the actual number of monomers that are attached into this forming polymer, right? So this is the total number of monomers, but now in the state of belonging into the polymer. All right. So what am I saying, basically? Well, through the process of decay that I just mentioned, what's going to happen is that this is going to flow back into the pool of monomers, right? This is going to happen at rate delta. On the other hand, what's happening is that this pool of free-floating monomers will eventually go into the polymer, right? So basically the polymer is capturing these monomers and attaching them on its ends, but in doing so, it actually acts as a self or autocatalytic factor. So basically, the more polymer there is, the easier it is for it to keep capturing these monomers. This is the simplification, the model that we are going to use in order to explain how, depending on the constants that are going to govern this system, we shall see different types of polymers emerging, right? So in this case, for the capturing or absorption of monomers, we are going to use a rate of constant K, or a constant rate, namely K. All right. Importantly, we have said that the total number of monomers is fixed, right? We are calling it N. Therefore, we shall have that this is conserved, right? The free monomers and the total number of monomers that are part of the polymer should all the time be a constant value. Great. So now that we have this scheme and we have some of our constraints, such as this constant population constraint, we can write down how the equation for the amount of monomers that are belonging to the polymer should look like. And very easily, we are quite familiar with these sort of equations at this moment already. And we simply need to account for the following. First off, this polymer is decaying at some rate. So, right, it's bringing some of the concentration down back to the free floating monomers. And this is happening at rate delta, and it happens also proportionally to the amount of monomers that are sitting in this polymer. This is the first term that we shall be looking at. The next term, it's not so straightforward because we do have capturing of the free-floating monomers, so this is going to increase the number of monomers inside the polymer, or if you want, belonging to the polymer. Therefore, there's going to be a plus sign. It's going to be governed by this constant K, but it also will be depending on C and depending on P, right? Yes. So this, again, is the total number of free-floating monomers, and this is the total number of monomers in the polymer. And this effect here, the fact that this is sitting right here, it's a reflection of this autocatalytic factor that we are saying it happens in the following way, right? So the larger, the more monomers that are inside the polymer, the easier it is for them to capture these free-floating monomers. Great. So now that we have this equation, we shall include the constant population constraint in it, and then try to find its fixed points and its stability, and make a short discussion of it. Right? So in this case, notice that I can use the fact that C is going to be N minus P from the constant population constraint, and I can just very quickly substitute it down here with the following. So this is going to be minus delta P plus K N minus P times P. So far, so good. We can still further simplify this in a way that's going to be useful for us. And for example, I could take K here as a general factor outside. I can also take P because everything is multiplied by P, right? And all I'm left with is going to be the following. So I have N, the total number of monomers, sorry. I have delta over K, right? Because here I'm taking a factor outside K, therefore I shall be dividing this by K in order to be appropriate here. And then just a last term that it's this P, right, is squared right here with a minus sign, and then K is outside, so I'm taking one of them outside, but then I'm still left with this term P. So this is very simple, and it allows us to already see what different fixed points this system shall display, right? Because here I have one root of the right-hand side of the ordinary differential equation, and here I have the other root. And as a matter of fact, I can just go up here and say, great, one of the fixed points shall be the trivial one, which is 0, right? And the other one is going to be the 0 of this root here, which basically corresponds to taking a minus sign in front of this, and we shall call it P1, right? And it basically is delta over K minus N. Great. I'm sorry, minus delta over K plus N, of course, because this already carries a minus sign, so therefore this is exactly what we should expect. Great. Now we want to observe, or we want to study the different stability properties of these two fixed points. But as we have done before, the easiest way to do this is to actually look for the stability of the trivial fixed point, because once we have that, we know that from it being a one-dimensional system, one variable problem, then the stability of the trivial fixed point is going to immediately give us the stability of the non-trivial one. So in this case, we can just move on by looking at the Lyapunov coefficient for this for the trivial fixed point. Remember, this is going to be the derivative of this equation, right? So we can quickly do it. As a matter of fact, we can do it down here because we know that this is going to be carrying a p square, right? And therefore, this term, when we substitute by the trivial fixed point, that's the nice thing about studying the trivial fixed point, this is going to cancel. And all we're going to left with is going to be this term times the k, and p is going to vanish from the derivative. So if this is a bit costly for you to see, please do it yourself, and you'll see that it's not so difficult. So I'm skipping a few steps here, but not that many. Notice that I am left with this, right? And now I can debate what's the stability of this fixed point. So immediately I know that if n is larger than this division here, delta over k, then this is going to be an overall positive factor, right? So if n is larger than delta over k, in other words, and I'm going to use this now, k is larger than delta over n, right? Therefore, I know that in this situation, I'm going to have that p naught is unstable. Simply because this implies that this lambda is going to be larger than 0. So this is one of the regimes that we can look at. Naturally, if this is unstable, immediately I know that this must be stable for the same regime, right? I'm going to talk more about this in a second, but this should be something that we are already familiar with. This is also thanks to the fact that there's only two fixed points, right? If there were more, we could also perform this trick, but we should think a little bit farther, because each stable and unstable point should be according to their sequentiality that you see. On the other hand, we could have that n, the total number of monomers, it's actually a value that is smaller than this division here, delta over k. So if this happens, what we see is that if this is less than this overall term is going to be negative. Remember, when this is negative, this is telling us that the point that fixed point that we're looking at, it's a stable one. So what we are seeing here is that depending on and I'm writing again this as a fact, by looking at parameter k, which is the one that I'm going to be using after I'm writing I'm depicting the phase diagram or the bifurcation diagram, right? Yeah, basically, this is going to be stable now, and this is going to be unstable, right? So this is a very simple setup, because this is just an order 2 equation where we can obtain this stability very straightforwardly. Great. Again, so if I were to draw this in the real line, basically what I shall be seeing is the following, right? In the first scenario, where I'm going to now denote delta over n as k critical, in the first scenario, where k is larger than k critical, what we are seeing here is that this point, right, so this is going to be the line for p, this point here is unstable, therefore any position around this point, the trivial fixed point, is going to be escaping the trivial fixed point, and it's going to go to this one, right? And remember, this one is going to be positive, precisely because here, as you see, what we have is nothing but, mathematically speaking, notice, this is n minus delta over k, which is exactly what we had for the value of the non-trivial fixed point. Great. So here we have that this is going to be our attractor, right? And then on the other situation where k is smaller than kc, what happens here is that This is again the trivial fixed point, 0. But now, in this situation, remember, k less than k critical, which is this situation over here, implies that lambda of the trivial point is negative, meaning that this is negative, but this means that P1 is negative, and therefore, as such, it cannot be a physical term, right? Because it's sitting at the negative values for the total number of monomers belonging to the polymer, and that makes no sense. And as a matter of fact, what happens though mathematically is this is going to be an unstable point, and this is going to be our stable point. In this case, we can understand that for this specific regime, what we have is that there's not going to be viability of the polymer formation. Now we're going to do a bifurcation diagram, and we want to explain a little bit further. I'm going to propose you a very interesting exercise. So again, simply we have obtained, there's two very reasonable and simple scenarios here. Let's then draw the bifurcation diagram. Remember, this works as follows. I'm going to lay down here all the different values that I can attain for one of the constants, and I have already spoiled it for you, but the constant I'm going to use is going to be k, right? And on the other hand, here I'm going to write, or I'm going to depict, what's the stable fixed point that it's being governing the system for these different values of k. This is again called a phase diagram or a bifurcation diagram, depending on your taste. Great, we know though that there's a particular point, there's a particular value of k, which is this critical k, where things kind of interchange their stability, right? These two fixed points, they interchange their stability, and they actually, this is the same point at which, notice, P1 is going to undergo from 0 to positive value. It's going to attain a positive value, and actually it's going to jump to this other state, the state where P1 is the actual stable fixed point. So very simply, there's going to be, thanks to this critical value of k, which I'm writing it here, so this is going to be Kc. Remember, this is nothing but delta over total number of monomers in the system. There's going to be two regimes. The first regime is for when k is smaller than this critical k, right? In this regime, we know that the fixed point is all the time 0. There is no polymer. So basically here, I shall have that this is our fixed point. Great. Now, what happens for k larger than this critical k? Well, now we know that the critical fixed point is p sub 1. I'm going to write p sub 1 again right here, right? P sub 1 is n minus delta over k, and if you want, p sub 0 is simply 0. All right? Notice, what's the functional form of p sub 1? We know that in this region over here, p sub 1 is going to be the stable fixed point of the system, the single stable fixed point. But this is what? In terms of k as a variable, this is an inverse of 1 over k. Therefore, it's like a hyperbola, but it carries a minus sign. So if a hyperbola shall look like this, when there is a minus sign, a hyperbola shall look like this, right? And overall, if I take k to infinity, I know that I'm going to be left with this asymptotic behavior. P sub 1 is approaching n. So I know that whatever function I shall write here, this is going to stabilize at n. Naturally, because I could not have a polymer that it contains more monomers than the total number of monomers that exist in the system. If something different had happened, then that would be an indication that I might have made a mistake. Now that I know what's the functional form of this, I only need to write this or depict this schematically. I don't need to be very trustworthy to exactly the points or anything. Just understand that this is how this is going to be looking like, right? So this is an inverted hyperbola that it's saturating at n. Great, so this is actually our phase diagram or our bifurcation diagram. And I just want to explain a few things within this very simple setup that we have obtained from thinking about polymer formation in a very simply schematic way, and go a little bit further, because one of the interesting things that we have to understand from the study of dynamical systems is that when we simplify the model, sure, we are making a bunch of assumptions that maybe lead us further from what we shall observe in reality. However, this is not so bad because, on the one hand, it allows us to make simple predictions, qualitative predictions in this case, and we shall speak about more about this right now. But it also tells us, or it guides us towards complexifying the model and trying to see whether or how things shall go from this point onwards if we were to take a more realistic approach, right? So that's why sometimes it's very important to be able to abstract our system and consider something simpler, just as the thing that we have been looking at. So in this case, see what's happening here. We have a very clear distinction between two phases. In one phase, there's basically no polymer, right? So here, the total number of monomers belonging to the polymer seems to be 0. But what if I actually were to simulate this polymer formation scheme, right? What if I actually take on a computer simulation where I have monomers that can attach each other, right, with some probability values or some rates that are corresponding to having a k value lower than the critical k? Well, what should I see in this simulation? Should I see that no polymers formed ever? Well, this is not really the case, because randomness will generate some of this polymer. So if I am actually looking at my simulation now over time, right? And I here consider the variable of how many monomers are attached to each other forming polymers, I shall not see that this is a constant 0 value. What I should see is some stochastic behavior, right? That it's basically very pushed down to the 0, and overall I could say that overall this is approximately 0 all the time, but this is really what things would look like. In other words, if I made a picture of this simulation, then I should be looking at some tiny monomer, maybe dimer or trimer chains that are very unstable and very quickly go down to single monomers. So there's still going to be some tiny polymers, but they are very quickly going to disintegrate. This is the actual meaning of this state over here. On the other hand, if I am looking at this, right, from my simulation standpoint, meaning that in this case I should take the values of the simulation such that they correlate to the fact that this k should be a large value, larger than the critical k. Again, if I look at what's happening here, and this, for example, should be the value that is correspondent to our mean field, or this sort of general ordinary differential equation approach, I shall not see that this is a constant over time. As a matter of fact, again, randomness is going to make this fluctuate around this constant, right? And this is the total number of monomers that I shall see over time is going to be also oscillating around this value, okay? So it's important to bear in mind that this is a more realistic depiction of what should be happening. In other words, here, I'm going to have large polymers, sure, but they are not all of the same size. They are not all conserving this total number of polymerized monomers. Actually, things are fluctuating. This leads to the following conclusion, albeit I agree that this is only the thing that you have to take my word for it for now. But what then is happening right at this very interesting crossing where I translate or I basically change the different basin of attraction from no polymer formation to actual polymer formation? Something very interesting is happening at this critical point, right? As a matter of fact, if we again were to turn up the crank for our simulation, what we shall see here is that sure, we're still at this specific point, we're still very close to 0 value, quote unquote, on average, but now fluctuations have gone wild, right? And this is actually a very interesting pattern that emerges in many complex systems. And we shall see, for example, a very similar situation for things like the SIS model, or, for example, in brain neural dynamics or brain activity dynamics, right? Now, this is very interesting as well, because if we were to depict some sort of system for this, what we shall see is that now we have a very interesting variety of polymers of all sizes, right? Again, this would be if you were to take this example and jump it to the next level where you shall have some simulation environment where you allow polymers to form and so forth. This is really a much harder exercise to do than what we have done. But it is what we have done is already telling us something that we shall observe when we go and move onwards for this more sophisticated paradigm, right? Of being able to simulate or being able to work out some of the stochastic behavior. Now, before I end this exercise, let me comment two more things. And these sort of ideas of having a process that it catalyzes itself has been central to many of the discussions on the origins of life problems, right? In particular, Freeman Dyson was one of the, on the 80s, he was one of the guys who actually proposed the idea of this autocatalytic process. He was not the only one. There were others like Stuart Kauffman and many others. But he proposed a very simple approximation that very much resembled this process, where he argued that if you were to have some autocatalytic formation of polymers of some sort, you shall not be in this regime. Naturally, this makes sense because these are very short-lived polymers. These are very short-lived polymers or objects. They are very short-lived, and also they are not able to keep up producing or replicating this information at all. It's just something that it quickly decays, right? On the other hand, if you were saying, all right, so maybe in the origin of life scenario, we shall have polymers that are tuned, which parameters are tuned such that we shall be on this area here. He also argued that this would not be a proper way of approaching the first stages of life, because in this situation you shall have very large polymers that their basic feature is that they are very greedy, right? They keep on adding all the monomers that are around, and this both saturates the system. There's no monomers, there's almost no monomers left. They're all now belonging to the polymer, and therefore you have very little variability. And if there's no variability, you cannot start exploring different ways by which the system could allow or find specific structures that allow for it to evolve further. And therefore, he argued that if anything like this should be occurring at the origins of life, then you should be self-tuned, or you should observe or look for systems that are sort of self-tuned around this critical point, because in this critical point you do have a large variety of forms and configurations emerging from the fact that this is going to behave like that, right? In order for you to explore a tiny version of what I've explained over here, you have as an extended exercise a PDF that explains how you could go on and simulate something like this, a bit more simpler. And I would encourage you to go on and do it yourself. You can use whatever programming language you prefer and observe this sort of phenomenon in a much more deeper sense than what is allowed from our ordinary differential equation approach, right? And that's it.